Hello, and welcome to Vector's Virtual Code Quality Symposium. My name is Andrew Teylu, and I've been working at Vector for over 9 years. In my talk, we're going to discuss some of the research that my team has been doing about trying to bring stronger typing to C and C++ to hopefully make code be more maintainable and more robust. So let's set the scene and let's get in a time machine and let's go back to the 1950s and imagine that we're building a car. What materials might we use to build that car? Well, what's predominant and people know how to work with? It's steel. It's strong, it's robust, we can work with it. Let's jump forward 30 years to the 1980s, and what might we be using? Well, we might be using aluminium. It's strong and it's light. We might be using more plastic because it's malleable, it's customizable. So we've had increases in material science which have helped build better cars. Then let's jump forward to the 2020s. What might we be using? Well, we've had even more advances in material sciences, and we now have access to composites and carbon fiber. These are materials which are much lighter and stronger than what we had before, allowing us to build stronger, more safer cars. Now let's have the same situation, but we're being software engineers and we're writing software for an ECU, an electronic control unit. So we're in the 1980s. What data types are we going to use? Well, we're probably building for an 8-bit microprocessor, so we're probably going to be using 8-bit integer types. How about in the dawn of the new millennium? What might we be using? Well, we're starting to see the proliferation of 32-bit targets, so we're probably going to be using 32-bit integers. Finally, what about the 2020s? Well, we've now seen a great increase in 64-bit targets, for example, in ARM, which are now in everyone's laptops, phones, and embedded targets. So we're probably going to be using a lot of 64-bit integers. So the positioning of this talk is we've had these great increases in material sciences for physically building a car, but where has that been for software engineering? Yes, we've got more bits, but we've not necessarily got better types to work with and to represent our data. So here's an example of type systems at work. So we have a bit of C++ on the screen. We start off by declaring an enumerate type gears, which ranges from 1 to 5. We declare a global of that type, G current gear. We then have this function which assigns from an integer type into our enumerate type. Now, really handily, the compiler stops us here and says, no, I don't like what you're doing. This isn't valid. You can't go and do this. So this is type systems at work, and this is the type system stopping us writing stupid, bad code. Now, let's change this example a bit, and rather than using an enumerate type, let's just use an unsigned character type. And at the same time, I've changed our setGear function from taking an integer to now taking a signed 64-bit long type. If we make the assignment here from our 64-bit signed type into our 8-bit unsigned type, the compiler stays silent. It allows us to go and do this. It happily lets us have this data truncation and data loss. This clearly isn't great. So the purpose of this talk today is there something we can do better when it comes to writing our software that will allow us to mitigate some of these issues before they become real problems in fielded systems? So what might we want if we're trying to build something like this? Well, let's stay with C and C++. We've got lots and lots of existing code. We've got lots of legacy code. We also have an awful lot of tools and compilers to support it. Importantly, our engineers know how to read and write C and C++. But what I'd like to do would be to make the existing code base become a single source of truth for this better typing information. I also want to be inspired by Ada's strong typing. So Ada was a programming language developed in the 1980s by the US Department of Defense, and it has a really, really strong type system. Such a strong type system that it struggled to gain adoption because people thought they were continually fighting against the programming language, even though the programming language had their best interests at heart. Finally, we've got the cool kid of the day, Rust. Rust has made it acceptable from a developer experience perspective to have more compile errors. and have issues that occur at runtime to allow the language runtime to abort the program. So let's take inspiration from that as well. Now, some of what I've proposed, you might say, can't you do this with C++ contracts? For those of you who don't know, C++ contracts are a feature proposed in C++ 20. They then slipped into 23, and I think they might have been accepted into C++ 26 now. What they allow you to do is they allow you to add pre and post conditions to your function, and the language runtime will check those as it goes along. So again, we've got this set gear function, which we decorated with this precondition that says the gear that we are taking as our right-hand side of the assignment is correctly ranged for what we expect G current gear to be. Now, the disadvantage with C++ contracts is that you decorate a function, not a type. This then becomes a bit of a maintenance problem, because if you want to go and add a sixth gear to your car, you have to go and change all of these contracts. And it's not immediately obvious if you look at one particular variable, what should its range be? Now, if I could go and add C++ style contracts against types, and I could have them in C, I probably could stop my talk here and just say, go and use contracts. Alas, we can't, so my talk will continue. So what am I proposing? In the academic literature, there is something called refinement types. Refinement types are similar to object-oriented programming, where you have a base type and a derived type. In refinement types, the base type is the underlying data type that you're working with. So for example, for gears, it might be an integer. Then the derived type, or the refinement, is the restriction on that type to be a more specific type. So in what I've got here, we're saying gears is an integer, but it's only valid between 1 and 5. If we're doing this in Ada, it'd be really straightforward. We could just do type gears is range 1 to 5, and then Ada's type system would constrain us to make sure that gears never goes outside of 1 to 5. I previously showed you an example on a slide earlier on where enumerate types give us some of this. Now, one of the problems with using enumerates is you can't go and do arithmetic operators on it. What does it mean to add two gears together? And probably your current code isn't using enumerate types in place of integers. So it gives us a big maintenance burden if we want to go and move to go and use enumerates everywhere. So we're going to say enumerates aren't for us. So how do we then use these refinement types? These refinements end up becoming invariants across system execution. What this means is whenever a software engineer sits down to look at a bit of code, they can immediately know and understand what is the range of this variable that I'm looking at. I've got a gears, I always know it's 1 to 5. This then reduces the cognitive load on a developer because they are dealing with a restriction on the entire problem domain. This allows for easier reasoning. But it's not only for software engineers, it's also for tools. Now imagine that we have a tool that has found a static analysis warning in the code, but it only happens if a variable is greater than 200. Now the refinement type might say it's only between 0 and 100. So then that warning becomes a false positive and the tool can then ignore it. However, we do require some runtime support to ensure the invariants never get invalidated. This is because data can enter the system in a way which we don't have the correct typing on it, so we won't know if it's always correctly constrained. So inside of the code we're writing, we require runtime support to make sure those invariants never get invalidated. So far, I've spoken very much from a software perspective, but now I want to talk about your systems engineering activities. So if you go and talk to your system engineer about the system you're building, they will know what these ranges already are. They don't live in the software domain, they live in the real physical domain. They won't consider that a car could possibly go from -2 billion to 2 billion miles an hour, whereas your software engineer won't think anything about representing speed as an integer, which is implicitly them saying, I think it's valid for speed to be between -2 billion and 2 billion. Your systems engineers probably document their expected ranges in the system in something called an ICD, an interface control document, or a data dictionary. So what I've got is I've got a few examples of ICDs and data dictionaries, just so you can see how this data might be documented. So NOAA is the US organization for dealing with the seas and the weather. They have an ICD for their next generation weather radar. One of the particular fields here is reflectivity. and Noah have stated that reflectivity ranges between -32 and +95. So if we want to go and create a refinement type for that, it's very straightforward. When I say reflectivity, its base type is an integer. It ranges from -32 to 95. Now, the use of an integer here was my choice. Actually, what we could have done is we could have used a signed character type, because the range of this refinement type would fit inside of a signed character, so a signed 8-bit type. Here is a similar example taken from the data dictionary from NASA's Joint Polar Satellite System. And they have a field here which is allowable deviation. Allowable deviation, interestingly, is specified as being a 32-bit integer, but it ranges between 0 and 20. So it's really straightforward for us allowed to create us that refinement type. We say allowable deviation, its base type is an integer. It ranges between 0 and 20. I then got a snippet of the ICD from Rocket Lab's reaction wheels. Reaction wheels are devices in microsatellites to allow them to position and orientate themselves in space. Inside of the ICD, they've listed survivable temperature as being between -40 and 100. So again, it's straightforward to go and create our refinement type. We say x is an integer. It ranges between -40 and 100. What I really like about this example for the reaction wheel is it shows you how these refinement types bring you this situational awareness into the code to allow software engineers to have a reduced problem set. So let's imagine you're working on some code for the reaction wheel and you're thinking, do I need to worry about if this input is 1,000? No, it doesn't make any sense to consider temperature would be 1,000. That's outside the survivable temperature for the entire reaction wheel. So you can just stop thinking about problems like that. Finally, I've got the ICD from ICAO. ICAO is the organization that publicizes all the standards to allow you to certify about a plane in the air. For part of their telecommunications network, they specify that timeout ranges between 2 and 120 seconds. So again, I can create a refinement saying timeout is an integer and it ranges between 2 and 120. Okay, so I've shown you that your systems engineers have this data, but now we're going to talk about how do we embed that into the code and ideally make the code be a single source of truth for this range data. So how might we do it? A very straightforward way of getting this information into the code is to use self-documenting type defs. So for those 4 examples I've just looked at, I've created type defs. So let's look at the reflectivity one. So we've said type def 8-bit integer reflectivity, and we've documented that it ranges from -32 to 95. What's really nice about this is if you're using an IDE such as VS Code or Vim and it has an LSE capability, we get autocomplete and hover and syntax information about what it means to reason about these type defs with our range information. So here I've got a function set speed that takes a speed. If I go and hover over it, I can see that the range of a speed variable is between -20 and 200. Okay, so far so good. I've shown how we can encapsulate the operating constraints of the code that comes from our systems engineers into that code. This then provides that situational awareness for your software engineers so they know how should the code be used, what is the kind of information we're going to get passed in. I propose that this makes the code easier to write and maintain because you have less things to worry about because you know exactly how it should work. However, that's a very much a human side of it. What can we do from a tooling side of it to maybe get more useful errors and warnings to stop people writing stupid code before it gets shipped? So I've highlighted some really easy things we can do. One is don't mix incompatible types. So I've got a function here which takes a speed and it assigns it to a temperature. Clearly, that's not going to be correct code. So we can easily validate that those types are incompatible and flag them up at compile time. There is something called covariance, which says that a more specific type is an instance of a less specific type. So I've got an example here where I have a positive speed type which goes between 0 and 100 and a speed type which goes between -100 and 100. Clearly it's valid to pass in a positive speed to a function that takes a speed, but it's not valid to pass in a speed to a function that takes a positive speed. We can flag up areas where literals have been assigned to types that don't fit. Again, let's imagine we have a variable of a positive speed type and we assign -10 to it. Obviously, that's going to be wrong because -10 isn't valid as a positive speed. We can also flag up obviously wrong conditionals. Again, let's imagine we've got a type that ranges from 0 to 300, and there's a condition in the code that says if x is less than 0. If we see something like that, we immediately know something is amiss because the type system won't allow a variable of that type to be less than 0. So it means the entire body of the if is suspect and is actually dead code. Unfortunately, static checks are only part of the puzzle. Part of this is because of the halting problem. We can't decide everything, but we also have an instance where we need to have runtime checks when data enters the system. So we can't just get away with doing things statically. So where might we need these runtime checks? For example, when data enters the system, if we receive information from a human or we read from a sensor, we need to make sure that the information that's come in is compatible with the refinement types. We also need to check when we deal with arithmetic operators. So when we modify a variable, we need to make sure that we've kept it inside of its range. It's really important that these checks happen at conversion time, so when you make the change to a variable. This is because we need to ensure those invariants are maintained throughout the entire execution, such that whenever someone is working with the code, they always know exactly what the range of that variable should be. Now, what should we do when the type system is invalidated? Well, we've got a few choices. We could be like Rust. We could just crash or exit immediately and just terminate the program. For C, we could choose to long jump to some kind of safe state where we could reset the system. For C++, we could throw an exception and have some code higher up catch that exception and make some corrective action. Potentially more interestingly, though, is this idea about using modular arithmetic or saturation. Modulo is what your software engineers are used to when it comes to dealing with unsigned variables. So if we have an unsigned character type and it ranges between, it's gone up to 255, and then we add 1 to 255, our software engineers know that that will then wrap around to going to 0. Saturation is like what we have with floating point, where we have extremal or maximal values which become sticky. So for example, in floating point, when we reach infinity, if we add 1 to infinity, we stick on infinity. For saturation for refinement types, and we take our gears example, we might say when we reach gear 5, if we add 1 to gear 5, we stick in gear 5. Now, using these refinement types for indexes into buffers becomes very interesting. So here we've got an example of a buffer variable which is 500 characters long, and we've created an index type to index into that buffer. Now, as long as we always use our ranged index type to index into that buffer, we are never going to lead ourselves to an out of bounds read or write. This is because whenever we make changes to that index, if it does go outside, either the program's going to crash before it, or saturation or modular arithmetic are going to change the value of the variable to make sure it is always inside the correct range. Now, neither of those choices are correct. They're still going to be doing something that you don't expect the program to do, but it's less dangerous than creating that out of bounds read or write. I went and pulled up some existing vulnerabilities from the US organization MITRE, who track vulnerabilities in software, to see the kind of problems we have. So there were over 7,500 vulnerabilities listed as out of bounds. So as I've just shown you, we could use refinement types to make sure that we never have indexes that are out of bounds. There were then over 3,500 related to integer, overflow, and underflow. Now, when these are vulnerabilities in the real world, it's because it hasn't been specified what the behavior should be. But with our refinement types, we could then say, this is what the allowable range of those variables are, and here's what should happen when we have under or overflow. We've then got over 250, which are about ranges. And again, we can create refinement types to specifically say what is the range of a variable, and then what should do if that range gets invalidated. When we think about software safety standards, for example, in automotive 26262 or in avionics DO178, we often refer to boundary and out of range testing. This is where we must test a function with the extremal values of what can be expected. Now, if you have a function that takes an integer representing speed, let's say, your developers might jump and say, oh, I should pass in int min or int max to this function. This is actually doesn't make much sense because you are testing the physical range of the variable, not the expected use case of how the system is going to work. Whereas if you go and use these refinement types, it then becomes very explicit to a tester or a software engineer what kind of values we should use to make sure we're testing the right behavior of the software. I wanted to highlight a few tools that allow us to work with these kind of refinement types or just give a stronger type safety. One of them is undefined behavior sanitizer, or UBSAN, which is something that's built into Clang and GCC. Now, this is tangentially related, but what UBSAN does is it allows you to automatically insert checks against the physical sizes of your variables into your program, and then have the sanitizer will abort the program if, for example, you have underflow or overflow. The next three tools, SPARS, PCLint Plus, and Clockwork, these are all static analyzers which support a various mode for checking the compatibility between types. So this was the example I gave earlier where we assigned to a temperature from a speed. These three tools will allow you to check those kind of type usage. Then we have SSC Verifier. SSC Verifier is a static-only tool which does allow you to have refinement style types in C and have those be statically checkable. Finally, we have the vTypeCheck tool, the tool that my team builds, which allows you to do runtime and static checks for both physical, that's int, char, long, that kind of thing, and also refinement types. So what are my takeaways from this talk? Well, I've highlighted that C and C++ are still extremely widespread. I don't want to throw them away. I don't want you to go and have a whole rework. So let's stick with these existing code bases. However, just by introducing named types, we can create self-documenting, more explicit code. If we then go and add these refinements to the code, it makes the operational constraints clear, and it allows for easier development and potentially catching a class of runtime issues. That's made the code then be more maintainable and more testable. And finally, when you add this runtime support, it makes the code be more robust. And this brings me to the end of my presentation. Why is everything in? I think my main takeaways from my talk would be you can obtain stronger typing in your systems without doing a complete rewrite. What I proposed about using refinement types can bring greater situational awareness to your code. This situational awareness then allows your engineers and tools to be more effective. Finally, bringing this stronger type information to your systems can mitigate a class of bugs that can lead to safety and security weaknesses. I look forward to your questions and to meeting you in the question and answers. See you there.